Hello everyone. In this video we will talk about sequences and their limits. So first we should ask, what is a sequence? Let's get a definition. So for us, we're only going to be considering real valued sequences. We're not going to worry about other kinds of numbers. And so it's going to be a function from the set of whole numbers or counting numbers, 1, 2, 3, 4, etc., to the set of real numbers, which we'll denote as this blackboard R. So this is not usually how we end up thinking of sequences, but it will be useful. But what does this really mean? We usually think of a sequence as just like a list of things. So for instance, if I just list out these numbers here, say like 2, 4, 6, 8, etc. Well, this actually is a sequence, but how can we see this? So we can view this as our first term. And so we associate it to 1, right? It's where 1 goes. This is where 2 goes, and so on. And so in general, well, what are we doing? We're just multiplying by 2 every time, right, to get these. And so we would say in general that the nth term of our sequence is the value we get when we plug in n to our function. And so in this case, f of n is 2n. So in this way, this function defines a sequence. However, it's not the notation we'll use. We'll often write it like this. So a1 is 2, a2 is 4, a3 is 6, and so on. And then the general nth term of our sequence would be 2n, and we would label that a sub n. And so we see the connection here that a sub n is just the notation we use for the value of n when plugged into our function. Okay, so now we're going to look at this example in a couple different ways. So first, let's just list out some terms, right? So we can just plug some things in. So a sub 1, our first term of our sequence, is 1. a2 is 1/4. a3 is 1/9. And we get pretty small pretty fast, right? So a4 is 1/16, and so on. So this can be useful, especially if you see a list like this, for instance. You may want to translate to a general form. And so in this case, you could just kind of see perfect squares showing up the denominator and come up with the general form of 1 over n squared. But we're often concerned with limits. And so we can see pretty quickly, right, that these things are getting really small and heading towards 0. But when talking about limits, right, when we just dealt with normal functions, we often use graphs. And we can graph sequences as well. So in this case, the graph is going to be different than the graphs you're used to because we're only plugging in integer values, right? And specifically positive integer values here. So if we label this, 1 and 1/2 here, so as we start going out, well, we have a dot at 1, 1, a dot at 2, 1/4, 3, 1/9, and 4, 1/16, and we're already getting pretty close to 0, right? And the difference here is that if you viewed this as a function, right, f of n is 1 over n squared, and then f of x is 1 over x squared is kind of if you filled in all of the gaps here, right, and kept going. But for us, our sequence, we're really just looking at the integer points. So now, we said this seems to be approaching 0, and we want to talk about limits in general. So let's get the machinery to be able to talk about this. Let's define what it means to be a limit of a sequence. Okay, so given a sequence a sub n, the limit as n goes to infinity, or basically as we, go off and take our terms further and further down the line in our sequence, this limit is equal to L if we can get as close to L as we want by taking n large enough. Now, there's some ambiguity here, right? Because what do we mean by as close as we want? And also, what do we mean by large enough? So I think it helps to go through an example. So let's look back at 1 over n squared. So we claimed from the graph or just looking at the terms that basically if we take n big enough, if we keep going down the line in our sequence, this should approach 0. Okay, so how do we actually show this? Well, what's the idea? So we're not going to do it very rigorously, but I want to at least give the idea of what's going on. So again, if we graph this guy out, right, we got 1, 2, 3, etc. So what do we mean first by as close as we want? So this means basically we can set an error bound, right? So if I want to be within 0.1 of my limit, right, that's pretty close. I might be happy with that. Then I'm just going to draw in my error bound down here, and I'm just going to draw a little dotted line. So basically, if I'm within this strip of red, then I'm within 0.1 of 0, my limit, right? And so which points are actually here? So I mean, 1, we get 1, 2, we get 1/4, 3, we get 1/9, which is still just barely bigger than 0.1. But once we hit 4, we're at 1/25 or 1/16, which is definitely less than 1/10, right? And so basically, once we hit this point here, this is basically our threshold, right? So what do I mean by in large enough? So basically, past a certain threshold, we're always within our error bound, right? And so in this case, our error bound is 0.1. Once we hit n equals 4, the fourth term, we're going to be within 0.1 of 0, and it's going to remain that way, right? Because this is just constantly decreasing and going towards 0. Now, if I change my error bound, right, if I made it 0.01, then I may have to go a little bit farther, right? So if I have 0.01 as my error, and I want 1 over n squared to be less than that, well, what's got to be true? Well, you can just kind of multiply over and get that n squared has got to be greater than 100, and so n has got to be greater than 10, right? And so the less error you want, the farther down the line in your sequence you're going to have to go. But this is the more rigorous way of talking about what we mean by as close as we want and large enough. Okay, so for exercise 1, I want you to look at these two limits and compute them. So I think it's helpful to at least write out several terms, maybe graph as well, and kind of see what's going on. And you should also pay special attention to this -1 to the n and see what this seems to be doing as you take each step in your sequence, because this shows up quite often in sequences. Okay, so basically the situation is if we have our sequence and a function that agrees with our sequence at every integer point, basically, right, that f of n is equal to a sub n here, then if the function itself, with all the points in between the integer values, when those are filled in, has the limit L, then our sequence will also. So let's look at an example. So let's look at an, which is sine of pi n over 2 all over n. So we can check out some terms, right? So for instance, a1, I get sine of pi over 2, which is 1, over n, which is 1. So we get 1. A2 is going to be, we get sine of pi, which is going to be 0. A3, we're going to get 3 pi over 2 into sine, and so we'll get -1, but then over 3. A4, we're back to 2 pi, so again, sine is 0. A5, we're back to pi over 2, so we get 1, but our denominator is different, so it's 1/5. A6 is 0, and you can kind of see what's going on, right? That all of our even terms are 0, all of our odd terms are kind of bouncing back and forth. But if we want to talk about the limit, I mean, it would be nice to just use tools we already have. Because when we see like a trig function like this over n, I mean, this feels a lot like a squeeze theorem problem from Calc 1. So can we do that? Well, sure. You just let f of x be sine of pi x over 2 over x, and then you can apply the squeeze theorem, right? So the limit as x approaches infinity of f of x is going to be 0, because sine is always bounded between -1 and 1, and if you take each of those bounds over x, those both go to 0, and so this is squeezed by two things that go to 0 and thus must be 0 itself. And so what's going on graphically here? Well, our blue points are basically the points of the sequence, and then our red graph is the one that actually is tracking what's going on, right? And it basically just looks like the sine curve that's getting kind of oscillating, but getting smaller and smaller in terms of amplitude as you go to the right. Okay, and so basically if the limit of the red is L, then the limit of the blue is also going to be L. So let's do one more example to show, again, why this is nice, because that one, at least graphically, you could kind of see it because plugging into sine isn't too bad if you choose the right things. But what if we saw this one? So if we saw the limit as n approaches infinity of n plus the natural log of n over n squared. This looks awful. I don't really like plugging things into the natural log without a calculator, and I would still like to know what's going on here. So I just define my f of x, right, to be x plus the natural log of x over x squared, and I look at its limit. Well, what happens here? So my top's going to infinity, right, because each piece is. My bottom is also going to infinity. And so now, since I've gone to a whole function of real numbers, this guy is continuous and everything, I can just talk about L'Hopital's rule, right? And so by L'Hopital's rule, this is the limit as x approaches infinity of 1 plus 1 over x all over 2x. And so in this case, my top is going to 1, and my bottom is going to infinity. And so this has got to be 0. And so by our theorem, since this is going to be exactly our sequence when we plug in the integer values, this must be 0 as well. Okay, and for your second exercise, I want you to find this limit here, and you may want to, rewrite it in a different way that makes it a little bit easier to compute. All right, thank you for watching.